Good morning, everyone, and welcome to the first Virtual GEM workshop. The steering committee, the focus group leaders have been working really hard to make this happen, so we are excited to have you all here and to have such large attendance. I think people are still dialing in, but we need to start. So before we start, some very quick reminders. First of all, we are using the Zoom webinar function, so there will be no chat. But if you want to ask questions, you need to either use the Q&A feature or raise your hand. If you use the Q&A feature, the moderators will ask the question for you. And if you raise your hand, then you will be unmuted and you will be able to ask the question for yourself. So today we have several very exciting talks to listen to, and Raluca will introduce our first speaker.
Hello everyone, I'm Raluca Elie. I am the research area coordinator for the Inner Magnetosphere, and I have the pleasure to introduce you today our first tutorial speaker for the virtual GEM meeting. This is Professor Rick Chapell, who's going to talk about the impact of ionospheric plasma on the magnetosphere. Professor Chapell graduated magna cum laude from Vanderbilt University with a Bachelor of Science degree in physics, and he received a PhD in space science from Rice University. And as it happens with anyone that graduates magna cum laude, they become professors at their alma mater. Well, maybe not everyone. That being said, at Vanderbilt University, Dr. Chapell holds a research professorship position in the physics and astronomy department. And as an educator, he has been actively involved in teaching and research, as well in science, communication, and outreach. After receiving his PhD, he worked at the Lockheed Palo Alto Research Laboratory before joining NASA in 1974. From 1976 to 1985, Dr. Chapell was the mission scientist for Space Lab 1, a joint European-American shuttle mission. In December 1985, he was elected to train as an alternate payload specialist crew member for the space shuttle mission STS-45, which was carried out in March 1992. As the Associate Director for Science at NASA's Marshall Space Flight Center for an entire decade, from 1987 to 1997, he served as the chief scientist for the center. Dr. Chapell has directed research in solar terrestrial physics and has been a principal investigator on several satellite missions. As a scientist and spokesman for the space program, Chapell has been interviewed on NBC, ABC, CNN, and BBC. From 2002 through 2009, Dr. Chapell acted as the director of the Vanderbilt Dyer Observatory. He had authored more than 150 published scientific articles, and he has edited 2 books on magnetosphere ionospheric coupling. Among a multitude of other distinctions, Dr. Chapell serves as a member of the Phi Beta Kappa Society and the International Academy of Astronautics. He is a fellow of American Geophysical Union, and he has received the AGU Ambassador and the Richard Carrington Award. He has also received the NASA medals for exceptional scientific achievement and exceptional service. Without further ado, let's welcome Dr. Chapell.
Okay, Raluca, thank you very much. It's a privilege to be invited to be part of this. And I want to share some thoughts on the impact of the ionosphere on the magnetosphere. So let me share my screen here. Okay, can everybody hear me? Raluca, can you hear me?
Yes,
absolutely.
Okay, great. Well, this is a special occasion for me in the sense that this is the 50th year that I've been interested in this topic of the impact of the ionospheric plasma on the magnetosphere. And I guess over those years, I've come to find that, for me at any rate, and I think probably for many of us, science, the process of science is like putting together a 20,000 piece puzzle with no picture to go by. And so what we do is sort of like a detective story. We look for clues, we look for information continuously, and the clues become the pieces to the picture in the puzzle. And gradually with time, the picture gets more solid and more understandable, and knowledge advances that way. So my approach today will be to talk about three areas. First, I want to give a short history of the role of ionospheric plasma in the magnetosphere and sort of show you how our thinking has evolved on that issue. And then secondly, I want to talk about the ionosphere, the role of the ionosphere as a source for magnetospheric hot plasmas. And I want to touch on the interaction between the cold plasma of the ionosphere and the hot plasmas, particularly the inner magnetosphere, and then talk about how the ionospheric plasma affects reconnection. So this image is sort of the way we were when the space program began with the launch of Explorer 1 and Dr. Van Allen's experiments on the radiation belts. We then began to be able to send spacecraft farther away from the Earth, and we realized that there was a magnetosphere and a magnetopause, and that the solar wind drove things in the sense that it flowed past the magnetosphere, made its shape, and then that solar wind plasma gained access to the magnetosphere, either through the cusps or through the flanks. And then this image shows the radiation belts, the two radiation belts. In addition to the particles in the solar wind, the sun's EUV shines on the upper atmosphere of the Earth and makes the ionosphere. So we have the thin ionosphere that surrounds the Earth, and the ionosphere is basically available in places where the sun shines on the atmosphere. And we get some effects in the ionosphere that I'll talk about later. But in these early years, we were focused on the solar wind plasma, how it affected the magnetosphere, the radiation belts, which initially we felt were formed by cosmic rays hitting the atmosphere, and then the resultant dynamics of the protons that were formed out of that. We studied the aurora and the plasma sheet and the ring current, which we thought were caused fully by the solar wind access. And there was one anomaly in the magnetosphere back in the early days, and that was the plasmasphere. This is a figure from a paper that I wrote back in 1972, but it just shows that the plasmasphere, the plasmasphere is an upward extension of the ionosphere, and the particles in the plasmasphere look just like the topside ionosphere, H+ and He+, cold, few EV. And then we began to see that the plasmasphere was dynamic depending on the convection field. In quiet times, the plasmasphere got larger. In more active times, when the convection field increased, the plasmasphere was mashed in on the back and then stretched out in the dusk sector, either in a plume or detaching plasma, so you could peel plasma off the plasmasphere. So this was an idea of dynamics, and I'm going to come back later on and talk about what this can do to reconnection out at the nose of the magnetosphere. So we had no idea in those early years, I'd say the first 10 years of space exploration, that there was any chance that the ionosphere, we never thought about the ionosphere as a source for the magnetospheric plasma, because the solar wind seemed to do that quite well. And then there was what I call the big event, and it was a paper that Ed Shelley and Dick Johnson and Dick Sharp wrote. I was at Lockheed then at that time, and they measured O+ ions which had to come from the ionosphere, and they were energetic. So all of a sudden, the ionosphere came into play in this 1972 time period as a potential source of ions, more energetic ions for the magnetosphere. And one might add, we could have asked back then, well, what about the H plus? Is it getting energized into a contribution to magnetospheric plasmas? And we didn't go there because the solar wind was a convenient answer to that at the time. Also, in this period of the early 70s, there became an enhanced appreciation for how the cold plasma in the magnetosphere could affect the warmer plasmas. This is a figure from a paper that I did with Richard Thorne, in which we measured the plasmasphere and the ring current from the OGO spacecraft. And what was found was that where the ring current overlapped the plasmasphere, in the dusk sector particularly, we got a stable auroral red arc at the foot of that plasmaspheric field line. And Richard suggested then that there was some interaction between the hot plasma and the cold plasma, which created ion cyclotron waves, which then affected the ring current energetic protons and caused dumping of energy into the atmosphere. And that was a good answer, in addition to later Keith Cole pointed out that there could be charge exchange and heating with that too. But this was a case in which the cold plasmasphere was affecting the dynamic energetic ring current. So in that same time period, there were a number of things that happened which showed a different thing was going on in the magnetosphere. First of all, Peter Banks and Tom Holzer wrote a paper about the polar wind. An idea or theory that on the top side of the ionosphere, where the oxygen O+ is dominant, the electrons can ride a little bit higher than the O+ and give a charge separation electric field on the top side of the F region. And that charge separation electric field could accelerate the minor ions up out of the ionosphere. The minor ions being H+ and He+. And they theorized that they not only would accelerate out, they would be able to escape the ionosphere and they would go supersonic. They'd have supersonic flows out of the ionosphere into the magnetosphere. These were measured by John Hoffman about a year later. And then we had a period where there was a great interest in studying the polar wind, how it fills the plasmasphere, and how it flows out into the magnetosphere. And also the polar cusp. We realized there was upflow from the polar cusp as well, but the process there is a very different one, because the polar cusp, in order for the ionization to flow out of the polar cusp, requires energy in. So you needed wave energy coming in and particle precipitation energy coming in to heat the ionosphere and the polar cusp. And when that happened, O+ would flow out, whereas in the polar wind, it's only H+ and He+. But in the cusp, you could have O+, H+, He+, and even other ion species, heavy ion species, that flowed up out of the ionosphere. Then, of course, in the auroral zone, you have that as well, where you have precipitation on the night side and it energizes the ionization. It can flow up out of the ionosphere. There were a number of missions, Dynamics Explorer, Akebono, Polar, Cluster, that looked at this flow of ionization out of the plasmasphere. So this is a piece of data from Dynamics Explorer from our RIMS instrument there, which was designed exactly to look at just the low energy plasma with energies from a few eV to 50 eV. And there's a problem with looking at the polar wind, which is that the spacecraft charge usually positively. And if the polar wind energy is only a few eV, the spacecraft charge can get high enough that you can't see it. It won't get to the spacecraft. So on RIMS, we had put an aperture plane around the instrument, and the instrument was looking radially outward, and it had heads that looked out either end as well. And this shows you what we saw. we varied the aperture bias around the instrument aperture. Here's -4 volts, 0 volts, -8 volts. We cycled that through, and when we had the negative bias on the aperture, we could see the polar wind. So the spacecraft is spinning, and each time it looks down the field line, it sees the polar wind flowing up with the energies and the flow velocities that you'd expect. This is HE plus, this is H plus down here. But it's just a reminder that if you're going to look for the polar wind, and I'm going to come back later and tell you the polar wind is an extremely important supply mechanism for the magnetosphere. If you're going to look for the polar wind, you're going to have spacecraft potential control so that the polar wind will actually get to the spacecraft. The DE instrument measured these low polar wind outflows. It also measured accelerated polar wind, and it measured auroral zone and polar cusp as well on the low energy end. There was a lot of this, and we were surprised at the degree, the amount of outflow. This is a figure from Mats Andre and Andrew Yao that looks at the total outflow of particles with energies from a few eV up to tens of eV. And you can see measurements from Akabono, DE, and cluster. And basically all three spacecraft saw this outflow. This is total outflow of 10 to the 25th to 10 to the 26th ions per second. It's a huge amount of ionization that's flowing out of the ionosphere, and it's flowing out any place that the ionosphere is sunlit, where the F region is generating the polar wind. So we ask ourselves, if there's this much flowing out, is that enough to fill up some of the regions of the magnetosphere? And this is a figure from a 1987 paper that we put together. And what we did is we used measurements from Dynamics Explorer and Akebono that measured how much was flowing out of the ionosphere. Of course, in the cusp, if you have oxygen, helium, and hydrogen at the same energies, the hydrogen will flow farther back in the tail. You get this geomagnetic mass spectrometer effect. But in the lobes, you couldn't see any of this because the spacecraft we could measure it down low, but the spacecraft in the lobes were charging tens of volts positive and could not see any of this outflow. But we said, well, let's take the total outflow and then estimate how far back it goes, just using a magnetic field model and a convection field, and then calculate what density we'd find in the plasma sheet region based on just that ionospheric outflow. And the answer was, and this is another clue, there was the densities that you could get from just the ionosphere by itself were what you measure out there, a few tenths to 1 ion per cubic centimeter. So there were enough particles coming out of the ionosphere to make the plasma sheet and the ring current. Down low, the outflow fills up the plasmasphere and then it drains back again. So a day-night type thing. The next clue, which was almost amazing to think about, was some work that Dominic Delcourt did, in which in his PhD thesis, he developed a program to track the ion trajectories that left the ionosphere and to follow where they go and watch how they get energized. And this is a figure that's from Matthew Huddleston's PhD thesis, but I want to take a minute or so to explain this to you, because this is a critically important clue to the idea of how the ionosphere can supply plasma to the energetic plasma regions of the magnetosphere. In this figure, we're looking from the side. Here's 20 RE sunward, and it goes to about 60 RE downtail. And the ion leaves the ionosphere with polar wind type energies. And so a few eV up to 10 eV. And the convection field carries, and it follows the magnetic field lines. The convection field and the magnetic field lines carry it back into the tail. It gains a little bit of energy. When it gets to the midplane of the tail, where the magnetic field lines are distended or stretched, the ion will have a quick turn in the magnetic field, and the centrifugal force will cause it to drift toward dusk. And drifting toward dusk means that it's drifting in the direction of the crosstail potential, and it gets energized. So in this panel, we're looking down on the top of the magnetosphere. Here comes the ion out of the ionosphere, then it gets energized. And in this case, it gets betatron accelerated as it drifts on in, and it becomes the ring current. Same particle. So here's the energy for the particle along the trajectory. It starts off at 10 eV, picks up multiple tens of eV until it, after an hour and a half, it gets to the plasma sheet region where it's energized to above a keV because of this drift, crosstail drift in the 50 kilovolt crosstail potential. And then it drifts inward, it betatron accelerates, gains more energy, and by the time 2.5 hours is reached, and up here, that's when it gets in this region, it's the ring current. So the aha moment in this is that not only do the ionospheric particles, which start as polar wind, make it to the magnetosphere, but they're energized as they do that, and they move through the magnetosphere and make different regions, the plasma sheet, the ring current, etc. Now, Matthew did something extremely interesting in his thesis, and that was to calculate where the particles go and then what sort of region do they make. So on the left is a look at this was the southern hemisphere, from the pole to about 60 degrees invariant, and he has divided that into different bends in which the polar wind, now this is from the polar spacecraft, so it was in a polar orbit measuring the top side of the polar wind flowing out of the high latitude ionosphere. So these different bends tell you something about the characteristics of the polar wind that were measured flowing up out of those bends. And there was a range of pitch angle of a few degrees and a range of energy of a few electron volts. So for each one of these, he then did the trajectory that I just showed you on the previous slide and asked the question, where would it be in the magnetosphere that ions that start with polar wind energies have energies that are increased to in excess of 500 eV and fall in the range of 500 eV to 5 keV, which is sort of the range of energy of the plasma sheet. If you start with these measured outflowing polar wind and do the trajectory and ask, where is it that their energies get to the energy range of 500 eV to 5 keV, this is what you get. So this is the region. This is looking at the magnetosphere from the side. It's about plus or minus 5 Earth radii in thickness, and it's 55 Earth radii in length. And if you look down on it from the top, this is what it looks like. That looks an awful lot like the plasma sheet. And the particles that are in there that started as polar wind are of plasma sheet energies. So that's a pretty eye-opening sort of phenomenon to be able to start with a polar wind, let it be accelerated by the crosstail electric field and the different drifting that it goes through, and find that it makes a region, all these particles taken together make a region that looks like a plasma sheet. So in addition to just the plasma sheet, you can do this same sort of tracing, and Matthew did this for a lot of different places in the high latitude or 60 degree up to polar hemisphere, and see where they go. And this figure shows you an idea of that, because the polar wind is always flowing out, and depending on what's happening with the solar wind IMF BZ, then the ions will flow out. If it's a northward BZ, where there's not much convection going on, all of the polar wind that flows out of the ionosphere goes out of the tail. As the convection field increases, then it will be convected into the midplane of the tail. And depending on where it interacts with the midplane, that shapes what it becomes in terms of its energy. If it goes pretty far back, it's like the trajectory I showed you a while ago. It becomes the plasma sheet, then it drifts in, becomes the ring current. If it goes back not as far and more on the downward side, it's not accelerated as much, and it drifts around the dawn side, becomes the warm plasma cloak. And then down in here, of course, is just the polar wind filling filling the plasmosphere and then being drained out. So this is a big thing I'm asking you to think about. The lobe is filled with outflowing polar wind all the time. So it's not like there's nothing here and something has to sneak in. It's there all the time. And to show you a couple of examples of that, this is a set of measurements made by the cluster spacecraft group, who used 4 different instruments to measure the orientation of the wake that was flowing past the cluster spacecraft when it was in the lobes. And you could look at they could look at the direction and the characteristics of the wake and tell what the ion flow was, even though it couldn't be measured directly by the instruments because it was polar wind and it was very cold and the spacecraft was charged, but they could derive what the flow was. And this is the cluster orbit with an apogee of about 20 RE. We're looking, the sun is off to the right, and the portions of orbits where they see the ion flow are color coded. So red is 100% of the time, blue down to 0. So there's a lot of times, or most of the times, in which in the lobes, this cold plasma, its polar wind is flowing out. If you look down from the top, you can see that here's the Earth and sun to the right. It's filling the lobes all the way across the lobe. And this is looking from behind back toward the sun. You can see it up in the lobes. Now, in addition, there's the polar cusp plasma, which is flowing out. And that's oxygen, it's O+, He+, and H+. This is some work from Lynn Kistler that looks at what you see in O+ from cluster. And this is a cluster orbit through the center of the tail. Here's the northern lobe and the southern lobe. And then over toward the dawn side in the tail and over toward the dusk side. Again, the 100% is red, 75% yellow. And you can see the ions are coming out of the polar cusp and flowing across the polar cap through the lobes, in this case, and getting to the tail. These show different levels of activity, but I won't go into the details on that. So constantly, there is polar wind flowing through the lobes and polar cusp ions flowing through the lobes. Stain Holland, working with the cluster data on the polar wind, put this figure together, and I want you to look at this and think about this. What it says is that depending on what the BZ southward component is, the ions go different places. So in northward BZ, the ions flow out of the ionosphere and high latitude ionosphere, and they flow down the lobes and they go out the back of the tail. They don't contribute to the midplane region. But as the solar wind goes southward, the magnetic component BZ goes southward, that puts a convection field across the magnetosphere, and the ions start being drawn into the midplane, farther down the tail. And then as BZ increases, then they get drawn in. There's stronger convection field, and they get drawn in out of the lobes into the midplane. Also, the polar cap gets bigger, so the amount of stuff that's flowing out increases just because of the polar cap increasing. So the important thing here is 2 takeaways. One is that the lobes are full and the ions will flow out of the end of the lobe, out of the tail, if if the BZ is northward. But once BZ gets southward, they're going to be pulled into the midplane, and they're going to get energized if we look at those trajectories that I showed you earlier. And another important thing is that they can get into the midplane very quickly. We don't have to wait for them to flow all the way from the ionosphere. The lobes are full all the time. And so as soon as BZ goes southward, the lobe ions the polar wind basically is going to be pulled into the midplane, and we know that it can be energized there. So now we've got a different situation in terms of looking at things. Certainly the solar wind is still a key element, and of course the solar EUV that makes the ionosphere. But there's plasma being supplied from the ionosphere now, and it's flowing up into the lobes. And when BZ goes southward, it can get into the midplane very quickly. And so it's a combination of what the solar wind magnetic field is doing, the BZ, and the ionospheric supply. Now, there's still solar wind that gets in there, most likely, but the amount of ionospheric plasma, which is already inside the magnetosphere, is extremely large. You can model this, and Dan Welling and Aaron Ridley did a paper where they used an MHD model of the magnetosphere, and they allowed sort of an open boundary condition at the bottom so that the model could pull into it the ions that it needed to basically make the equations work correctly. And they then separated ions that came from the ionosphere, that's these blue ones, from solar wind ions, the red ones. On the left-hand side is southward IMF, and you can see that this is looking at the magnetosphere from the side now, that this area is completely full of ionospheric plasma. If you look down from the top, the inner magnetosphere out to about 10 RE is all ionosphere, and then the middle part of the tail is ionosphere, dominantly out to, in this case, 40 RE. In northward IMF, looking from the side, it's a very different thing. The solar wind gains access into the magnetosphere back in the tail, in this case, 20 RE or so. And the ionospheric part is basically not allowed into the tail. And if you look down from the top, again, the ionospheric part is close, and the tail part, looking down from the top, outside of about 10, is solar wind. So there are cases in which the solar wind is there, but there are also cases in which the ionosphere is extremely strong, and the ions are carried into the midplane and can become the plasma sheet and ring current. Now, interestingly, this is about where we are now in our thinking, but I would submit that there are still a lot of people in the community who think that the ionosphere can contribute O+ to the magnetosphere, but not much of anything else, that all of the H+ and some alphas and some high charge state oxygen, all of the H+ comes from the solar wind. And that's just not the case. But unfortunately, we can't measure the difference between H+ that comes from the solar wind and H+ that comes from the ionosphere. They look exactly the same. And the only way we're able to tell anything is to do a proxy measurement where we measure the ratio of the alphas to the protons and compare that with the solar wind. And that's a good thing to do, but that it's fraught with a lot of challenges of interpretation. And with the way this is showing, there can be a dramatic change depending on the IMF BZ, a dramatic change in the contribution of the ionosphere to the compared to the solar wind. Now, one thing we can do, and I just want to advertise a paper that Alex Glosser is going to give tomorrow, and I encourage you to listen to that. Alex has been able to separate, with using multi-fluid techniques, he's been able to separate the the ionospheric H plus from the solar wind H plus and track those separately through the model. And in doing that, he's able to tell the relative, as a function of time, let's say through a storm, he's able to tell how much the ionosphere is contributing versus how much the solar wind is contributing to the plasma populations. And I won't steal any of Alex's thunder other than to say that in the event that he models, and he has outflow model of the polar wind, he has a plasmasphere, he has a ring current model, he has the auroral zone. All of that is feeding ionospheric plasma upward, and then he has the solar wind access from the outside. But in the case that he works, it ends up that the ring current is dominated by the ionosphere. The amount of H plus in the ring current is about equal to the amount of H plus, ionospheric H plus, about equal to the amount of solar wind H plus, but then the O plus is dominant and it's out of the ionosphere. So in the case that he'll show you where he can separate, I call it the red and blue H plus, the ionosphere is extremely important there. Just as to circle back to the trajectory that I showed you that Matthew Huddleston used in his work on polar, this is a streamline in Alex's model after it has been set up and is running its case. And this shows, in this case now the sun is off to the right. In the trajectories I showed you, the sun was off to the left. But so here in the ionosphere, afternoon ionosphere, here comes a polar wind ion, and it's following the streamline flow basically of the model. And the color tells you how energetic it is. And it starts off at 10 eV, flows up, out across the polar cap, through the lobe, until it comes back to the midplane where the magnetic field is distended and it gets its centrifugal drift that causes it to pick up energy, and it jumps immediately up to a keV and drifts back in, and then ultimately gets to 10 keV as it becomes warm plasma cloak and ring current back in the inner magnetosphere. So this is a particle, again, that starts in the ionosphere as a polar wind particle and ends up contributing to those regions. So I want to shift gears for just a minute and talk about the idea that the cold plasma in the inner magnetosphere is a very important element of magnetospheric dynamics because it affects the dynamics of the radiation belts. So going back to what we talked about a while ago, and this is another sketch, by the way, of a way to think about the magnetosphere, which is with the supply from the ionosphere feeding out into the magnetosphere. Here, these are polar cusp ions, and then the polar wind is blue. Polar wind makes the plasmasphere and affects the radiation belts, and it flows out of the polar cap and picks up enough energy to be called the lobal wind and be more like tens of eV. And then depending on what the convection field does, it can be carried into the midplane where it makes the plasma sheet and then the ring current. And depending on how far back it goes, if it comes in on the dawn side, it can make the warm plasma cloak. So, but in the inner magnetosphere, we're just dealing with ionospheric particles that look just like the ionosphere. They are a few eV in the plasmasphere. And those particles can affect the wave particle interactions and the waves that are generated. And this next picture is one that Richard Thorne put together several years ago. And it just sort of says there's a lot in the inner magnetosphere where the plasmasphere is found, and the plumes or detaching plasma, and in the warm plasma cloak that comes around this way. Those particle populations, the cold particle populations, are very influential on the waves that are generated. Hiss, chorus, the ion cyclotron waves, magnetosonic waves. The cold plasma, even though it doesn't carry a lot of energy, it affects the generation of waves and the propagation of waves and the absorption of waves. And so measuring the cold plasma effectively and thoroughly in the inner magnetosphere is extremely important, because it's going to tell you about how the waves are generated and how they propagate and then how they're absorbed. So when we do missions in the inner magnetosphere, we want to make sure that we're measuring the cold plasma, which is the direct upflow out of the ionosphere for this region of the magnetosphere. Now, the other effect that I want to mention and get you to think about this somewhat is that the ionosphere affects reconnection at least two places, at the nose of the magnetosphere and back in the tail of the magnetosphere. And here's how that happens. And Stephen Fuselier has a paper out just recently about the effects out here at the nose of the magnetosphere. So in the inner magnetosphere, where the ionospheric plasma is cold, the plasmasphere is there, and we have three ways that plasma can get out of the magnetosphere to the nose. One is on the dusk side of the magnetosphere, as I showed in that picture way back at the beginning of the talk. The bulge region in enhanced convection electric field situations can be drawn off as a plume or detached from the dusk sector, and it drifts out to the magnetopause, where it basically can enter the reconnection region. It's cold plasma, few EV, H plus, He plus. Also, the plasmasphere is trying to fill itself on the day side each day. When the ionosphere rotates into the sun, then the polar wind tries to fill up the plasma trough outside of the plasma pause. And that fills across the day side, but then a lot of that filling plasma will be carried out to the magnetopause nose and affect reconnection, adding cold plasma, again, cold plasma to this reconnecting phenomena. And then the third contribution from the ionosphere out here is the warm plasma cloak. These ions get there a different way. They come out of the ionosphere, they drift through the lobe, and then they drift into the midplane area in the dawn 10-15 RE back. And then they are energized with that interaction. They drift back through. They're double field aligned, they're oxygen rich. There's a lot of polar cusp ions being carried into this region. And the warm plasma cloak then drifts around the dawn side out to the afternoon sector and is carried out, can be carried, depending on what the convection field does, can be carried out also into the reconnection region. So you've got two sources of very cold ions from the ionosphere directly, and then you've got the warm plasma cloak. And that's a big effect on the reconnection rate at the nose of the magnetosphere. Now, the other area is the one back here, which is even more, requires a little more thinking. And that is, in the reconnection region back here, there could be some cold ions that make it in there, and there could be some heavy cusp ions that make it in there, and those will certainly affect reconnection. But the thing that we tend to overlook is that there may be a dominant input from the ionosphere through the lobes when the BZ is southward, a dominant input of ionospheric plasma into the plasma sheet. It gets energized very quickly by the curvature drift that I was talking about. So it doesn't look like the ionosphere anymore, but it is from the ionosphere. It's not cold either. It's hot, but it's ionospheric plasma. So there's terminology in there where a lot of times we call ionospheric plasma either heavy or cold. And those are both adequate, those are both appropriate descriptions, but it can also be, ionospheric plasma can also be hot, and it can be hot at plasma sheet energies, ring current energies, warm plasma cloak energies. So it makes a big difference on reconnection.
So Rick, if you could proceed to conclusions, so we allow some time for questions.
Okay, sure. In the substorm process, and this is in the talk and everybody can look, it's a suggestion of how a substorm might be caused by a combination of BZ and the ionospheric flow from the lobes into the midplane. So I'd encourage everybody to take a look at that. In summary, it's very clear that the ionospheric plasma plays a major role in populating the magnetosphere and affecting its dynamics. From the cold point of view, it's the polar wind, it's the plasmasphere, it's the plasma trough, the plume plasma, and the beginning of the lobal wind. In the energized, it's the plasma sheet, warm plasma cloak, and ring current. The lobes of the tail are filled with outflowing polar wind and polar cusp ions all of the time. It's sitting there and it's within 10 minutes, 20 minutes of the midplane. It does not have to come in from the solar wind. It's there and can fill the midplane. Together with the solar wind BZ, as I've said, the ionospheric plasma can be a major driver of substorms and geomagnetic storms. And then, of course, the cold plasma affects the radiation belts with wave particle interactions and reconnection at the magnetopause and back in the tail. We need to continue with new measurements of ionospheric outflow that can deal with spacecraft potential and that can measure the trajectory and energization and composition. And we need to do these multi-fluid models of red and blue hydrogen, the solar wind versus the ionospheric hydrogen. We need to do those. I want to dedicate this talk to Don Carpenter, whom I first started interacting with in the late 1960s, a wonderful man who was the first person to really ever realize that there were ionospheric particles out in the magnetosphere. And there's some references here for everybody's use. I really recommend that you read the Huddleston paper and Alex Glosser's paper, which is in the process now. So thank you very much. I'd be happy to take questions.
Thank you. So Seth, you are the moderator for this morning. Could you read the questions for Rick?
Sure, thanks Rick. It was a great talk. We do have a few questions in the Q&A. So I'll just ask them in the order in which they were received. We have one question is, what is the role of substorm injected O+ ions in ring current development?
So in the, let's go back up here. So in the ring current development, the O+ is likely to be coming from the polar cusp, and then its drift path brings it across the polar cap and puts it in the ring current region and combines it with H+ that's gone farther back and been energized. So you're going to get a combination, two ionospheric things from the polar cusp and from the polar wind. It can also come up out of the night side ionosphere where there's an aurora going on, where it gets energized enough it can move up into that region as well. So its role is certainly to enhance the impact of the ring current, the strength of the ring current, doing it by adding ionospheric ions from two different places, O+ and H+, and some solar wind ions as well.
Great, thank you, Rick. If we have time for another one, I'll ask the second one. As shown in the cartoon outflow with variable IMF polarity, outflow ions seem to do cross-field diffusion crossing closed field lines. If so, what is the time scale for that?
So the cross field, let's see, I'm not sure what they're referring to. In this instance, the convection electric field is what carries the ions to the midplane. And they are E cross B drifting basically from the lobe into the midplane. So there's not necessarily a diffusion other than that cross-tail drift. Now there may well be some diffusion as well, but the dominant way in which the lobe ions are carried into the midplane is through E cross B drift with the cross-tail electric field.
Great, thank you. And we'll do one more here. With respect to the cold plasma affecting waves in the inner magnetosphere, which is more important, the electron density or the mass density? One of these, electron density, always drops rapidly at the plasma pause. The other sometimes does not if there are a lot of cold O+ ions present.
So I'm not a good person to ask that. Clearly, the electron densities are important just in the wave generation mechanisms. and the mass density is as well. And as was pointed out, they both change at the plasma pause. I would say they change similarly because the ions are always, the plasmasphere ions are always basically neutralized. So there are electrons around. Whatever the density of the ions does, the electrons number density at least is going to do the same thing. But both of those, mass density and electron density, are very important in the inner magnetosphere.
That's great. Thanks, Rick. So that's all the time we have for questions right now. Just remind everyone that we do have a Slack channel as well going. So if you have any further hallway type discussions, to please submit those into the Slack, and we'll get Rick signed in there to ask any follow-up questions. And I'll throw it back to Vanya. Thanks again, Rick.
Thank you, Seth. It's a real privilege to get to be with the group.
Thank you. So let's proceed to our second talk for this morning, and Matthew Cooper will introduce our second speaker for today.
Morning, y'all. This morning I have the pleasure of introducing Dr. Lauren Blum. In her younger years, Dr. Blum was fascinated by math, science, and art, which unfortunately aren't three things you usually hear mentioned together, but thankfully Dr. Blum didn't let this faze her. In her early undergraduate work, she found her way into a space physics laboratory with the help of her then professor, Dr. Christina Lynch. The mixture of visuospatial reasoning, mathematics, and science hooked her, and after undergraduate, she spent a year working at Los Alamos National Lab. There, she decided to pursue a graduate degree in space physics. She attended Boston University for 2 years and then finished her PhD work at LASP in Boulder, Colorado. It's worth noting that up to this point, her career had gone coast to coast twice and changed in elevation by almost 7,000 feet. But who stops at 7,000 feet? She's now setting her sights on a new record for elevations her career takes her to. Since 2017, she has been the PI of the H-TIDES CubeSat mission, which will sit at geosynchronous orbit and investigate radiation belt particle dynamics. Please help me in welcoming Dr. Lauren Blum.
Great, thanks, Matt, for the introduction. Can everyone hear me okay?
Yes.
Yes, we can.
Great, I will try to share my screen now. Okay, so thanks again for the lovely introduction, and for to the students for inviting me to give this plenary talk. Today I'm going to talk about CubeSats and my experience with them, and then go into a little more detail about the current mission that I'm involved in, GTOSat. And I just wanted to acknowledge my co-Is and collaborators down here at the bottom who are involved in GTOSat, and then also past CubeSat missions that I've worked on. So when Matt asked me to give this talk, he suggested that I discuss my work on CubeSat missions and how the field of, basically how our field has been affected by these new capabilities and new platforms. And so I've been lucky enough to be involved in a number of CubeSat missions from development through launch and operations now. And I've seen their impact on our field and how they've grown within the space sciences, as well as magnetospheric and radiation belt physics in particular. So just a look at the numbers overall on the upper left here. Number of total CubeSats launched has grown exponentially in the past 2 decades. This ended, this is a few years out of date now, but you'll see a large proportion of these missions are from industry and companies starting up like Planet or Spire, who have launched constellations or flocks of CubeSats into low Earth orbit, often from the space station, depicted over here on the right. And so that's this green curve, these remote sensing or global imaging missions increasing dramatically and contributing to the number of CubeSat missions currently. But if you look, the purple line down here for science is also increasing, especially over the past few years. And so CubeSats have gained a more prominent role in science missions and in NASA, and also particularly in heliophysics and magnetospheric science. So since my area of research is radiation belts, this is actually where CubeSats have made a lot of progress in the past 5 or 10 years. And so there have been some wonderful missions that have flown and that are currently up, contributing to radiation belt science and making measurements of energetic particles from low Earth orbit. And this is probably an incomplete list and maybe a bit biased towards United States missions, but there are some upcoming missions as well from the US funded by NASA, as well as Korean Space Agency, that will expand our understanding of radiation belt dynamics, and in particular loss mechanisms of these energetic particles into Earth's atmosphere via precipitation. And so where these missions have been able to contribute, I think, is really in choosing targeted science questions to attack, and through providing complementary measurements to other currently operating larger spacecraft or ground stations or other platforms. And so through multi-point measurements, a lot of these CubeSat missions have studied the spatial and temporal scales of energetic electron precipitation into Earth's atmosphere, either through pairs of CubeSats like Firebird, AC6, and Elfin, or by combining CubeSat measurements with other platforms such as balloons in the barrel campaigns. The other area they've contributed in primarily is through conjugate measurements at low Earth orbit and deeper into the magnetosphere. And so with the Van Allen probes, or sitting in the equatorial plane, you can measure the wave populations and trapped energetic particles that may be scattered into the atmosphere and then measured at LEO. And so the plot over here on the right, the top figure is just the precipitation measured by one of the AC6 CubeSats, and then chorus wave amplitudes out at in the equatorial plane deeper in the magnetosphere measured by one of the Van Allen probes. And you see this very strong correspondence in amplitude as well as structure or modulation. And so through these conjugate measurements, particularly with Van Allen probes and LEO CubeSats, we've done a lot of work on studying radiation belt precipitation and loss. But with Van Allen probes ending in 2019, one question is what's next? And so this leads me into the mission that I've been working on and leading from Goddard the past few years, called GTOSat. And so this is a 6U CubeSat that was funded through the NASA H-TIDES program for about $4.3 million. And so we're currently under development and targeting a launch late in 2021. And what's different about this mission is that instead of flying in a low Earth orbit to measure the foot points of the radiation belts and energetic particle precipitation, we'll be flying through the heart of the radiation belts in an orbit more similar to the Van Allen probes, where we can measure directly the trapped population and the core of the radiation belt particles. And so this is where we get our name from, GTOSat, a geotransfer orbit satellite. And there's a large team of engineers and scientists working on the mission at Goddard Aerospace, University of Iowa, and APL. And we have 3 main objectives. The first is science. And so like most CubeSats, we want to get some great science and study energetic particles in the Earth's radiation belts. The second is to be more of a space weather provider. And so we'll be measuring the energetic particle environment and providing low latency or near real-time monitoring of this radiation environment. And then finally, more of a tech demo or technology advancement to demonstrate that you can use CubeSats and small sats to explore deeper in Earth's magnetosphere beyond low Earth orbit. And so I'll just touch on each of these 3 briefly. So the science goals of the mission are to quantitatively understand energy and pitch angle dependent dynamics of the outer radiation belt. And so we have three kind of measurement objectives or observational goals within this. One is to measure pitch angle distributions in differential energy channels. The other is to measure the phase-space density profiles, radial profiles throughout the outer radiation belt. And then finally, to measure energetic electron injections into the magnetosphere within geosynchronous orbit, which can act as a source for radiation belt particles. And these are just some figures from past studies. The one on the left is from Allison James et al. 2015, and this is just showing energetic electron measurements from a number of different energy channels on Van Allen probes. We have L shell on the y-axis, and then over a kind of 2-month period in time. And what you see is that while sometimes the different energy channels behave similarly, you can get dropouts and then enhancements across the full range of energies. You also get periods of time or events where you have pretty distinct behavior at different energy channels. So you can get enhancements in the hundreds of keV electrons and depletions at MeV. And so for studying the radiation belt's differential energy channels and this broad energy coverage is really important to more fully understand what's going on. And then similarly, the pitch angle distributions of these particles can give you insight into their dynamics and some of the physical mechanisms that can cause acceleration or loss of these electrons. And so you can get dramatic changes in the pitch angle distribution on timescales of seconds to minutes. And then you also can get very distinct different pitch angle distribution profiles depending on what wave processes or other processes are active on these electrons. So the other thing I wanted to just touch on briefly are the phase-space density profiles. And so these radial profiles and phase-space density are another clue that can give you insight into acceleration and loss mechanisms causing overall dynamics in the outer radiation belt. And so the evolution of these profiles can be used to indicate local acceleration or radial diffusion as a source of enhancements in the belt. You can also see signatures of fast local loss or scattering into Earth's atmosphere, as well as losses to the outer boundary or the magnetopause, just by looking at the evolution of phase-space density over time. And Alex Boyd has had some nice studies using Van Allen probe measurements that show often the apogee of Van Allen probes, which is at about 5.8 Earth radii, sees a positive slope to the particle phase-space density, but just beyond this, if you combine these measurements with Themis, for example, this is actually indicative of a localized growing peak just beyond the apogee of Van Allen probes. And so one thing with GTOSat that we'd like to look for with our slightly higher apogee of 6.6 Earth radii is to see if we can capture this, these peaks in phase-space density that occur just beyond the apogee of Van Allen probes. And then we also, he's also shown that you can get different profiles in the phase-space density for different energies or mu values. And so some are outwardly sloped while some have localized peaks. And so we'll be targeting mu values within this range where you see the phase-space density profiles changing slope. And then finally, we'd like to look at energetic particle injections into the inner magnetosphere. So with LANL and GOES sitting at geosynchronous orbit, you can track the azimuthal evolution of particle injections shown here. But you really want something sampling the radial extent of the injections as well. And so a geotransfer type orbit can be combined with these other geosynchronous measurements to more fully track energetic particle transport into the inner magnetosphere. So with that, what we had to do was think about what key measurements or what subset of the Van Allen probe's instrumentation did we really need to achieve these observational science goals? Because we can't fit the full suite of instruments that were on Van Allen probes onto a CubeSat. And so we chose 2 instruments to provide the kind of bare necessity measurements to answer some of these science questions. And so one is the relativistic electron magnetic spectrometer. This is a modified version of the MAG-ICE instrument on board the Van Allen probes. And so it's built by Aerospace Corporation, same group that built MAG-ICE, and led by Christine and Drew. And it's basically a magnet that bends electrons onto an electron detector, and then you get protons over in the bent the other direction. And so we'll be measuring both these particles, ranging from a few hundred keV up to multi-MeV energies. The actual size of the magnetic chamber itself is similar to the MAG-ICE instruments. I was surprised that we didn't actually have to miniaturize that much. It's really the electronics that got miniaturized to fit on the CubeSat platform. And so we'll have differential energy channels, 9 different channels kind of nominally, and configurable pitch angle sectoring, but over 8 pitch angle sectors per spin. And then we'll also have histogram data products. These are similar to what was provided on by MAG-ICE, and they can be used to remove penetrating background. And so Seth Claude-Pierre has some nice papers demonstrating how this technique can be used to clean up the measurements and remove proton contamination, and also provide very high resolution, finer energy channels at a delta E over E of less than 5% compared to the nominal energy channels, which are less than 30%. The other instrument is built by Goddard's Planetary Group, and this is a mini version of the Fluxgate magnetometers that have flown throughout the heliosphere to most of our planets and close to the sun. And so it's the sensor sits out on the end of a 4-segment boom that puts it about 1 meter away from the spacecraft to try to reduce the magnetic signatures from the spacecraft contaminating our measurements. And the boom deploys, it kind of sits in this cavity in the base plate and deploys out of that once we're on orbit. And we'll be sampling at 32 hertz in 2 dynamic ranges that cover basically the field strengths we expect to see out at apogee, and then also close to the Earth at perigee. And so this is to provide pitch angle information and measurements of the background magnetic field, but potentially we could get some lower frequency wave information as well. So the idea is that we're a sun-pointed spinner similar to the Van Allen probes. The REMS instrument looks out the bottom of the CubeSat, and then the magnetometer boom is on the other end. And so as you spin, you sample pitch angle distributions. And so we'll be spinning at a nominal rate of 8 RPM. And then when we're close to Earth, we'll downlink our, the bulk of our science data. And then as we traverse through the outer radiation belt, we'll provide a real-time beacon through the TDRS, a network of satellites, so that we can monitor the radiation belt real-time or with low latency for space weather purposes. And so the Van Allen probes provided a kind of experimental beacon, space weather beacon product that was used by NOAA's Space Weather Prediction Center, and for nowcasting or forecasting radiation belt fluxes, as well as rapid spacecraft anomaly resolution. And so GTOSat will provide a similar product. And there have been some studies recently showing why it's important to monitor the outer radiation belt, not just at geosynchronous orbit, but deeper across the radial extent of the radiation belt. Because while towards the edge of the outer radiation belt, the behavior is often very well correlated with enhancements or behavior at geosynchronous once you get deeper into the magnetosphere at L shells of 3 to 4.5, the energetic particle behavior can vary more significantly from that at geosynchronous. So you really want to know what's going on at all radial distances throughout the outer radiation belt. So I thought I'd talk a little bit about the spacecraft bus for people who are interested, because that's one of the main differences that we had to address when building this CubeSat compared to past low Earth orbiting CubeSats. And so we are building off the kind of lessons learned and experience at Goddard from the Dellinger 6U CubeSat that was launched out of the space station a few years ago now and continues to operate. And so we're a follow-on to this mission. And there are a few different approaches to building CubeSat buses. Some where you develop all the subsystems and components in-house, others where you buy commercial components and then assemble them and integrate them in-house. And then you can also now basically buy fully outfitted CubeSat buses and either just deliver your instrument or have them integrate the science instruments on board and then even do mission ops and things like that. And so we're sitting in the middle of these for GTOSat, where we've bought a lot of COTS components, but then are using the Dellinger lessons learned and systems engineering practices in-house to build the spacecraft. And so we have a lot of COTS components from a number of different vendors, our power system and batteries, the radio, and then a lot of the attitude control components are commercially available. And then we have an in-house developed CNDH board, command and data handling processor, as well as a special services card to kind of implement the needs that we had that were specific to the GTOSat mission. So things like deploying the magnetometer boom is handled by the special services card. And so for the bus, we've faced a number of challenges that are kind of universal to any CubeSat. You can see from this image, we're pretty densely packed. And so fitting within the mass and volume constraints of a 6U CubeSat was a challenge for us, but is a challenge for most missions. And then also power. We have these 2 large battery packs in white. But we also faced a number of challenges that were really particular to our mission and to our orbit. And so these are kind of the more, at least to me, maybe the more interesting areas and areas of development where I feel like I've learned quite a bit building GTOSat as compared to past missions. And so the orbit affects us in a number of ways. One are just the variable eclipse times. And so depending on what local time you're launched into, basically you can have, if your apogee is on the night side, you can have very long eclipses over 2 hours. And so you have to have the battery capacity on board to get through these eclipse times, and also be able to control the thermal environment on your spacecraft when you're getting very cold without any input from the sun. But if you're launched on the day side, you can have very short eclipse times. And so then, you know, all that battery power that you're carrying on board is really somewhat wasted, and you have to worry about getting too hot in that case. The other challenge with this highly elliptical orbit is for the attitude control system. So often CubeSats use magnetorquers, which rely on the background magnetic field strength to reorient or dump momentum from reaction wheels. And so our torquers only work when we're very close to Earth. So we really only have this very short, small fraction of our orbit where we can utilize them. And then once we move beyond about 1,000 kilometers altitude, we're unable to use the torquers very effectively in the low magnetic field strength. And then finally, maybe the more obvious challenge of this environment is the radiation background. And so what we want to measure, our science goals of the mission, is also what can damage us. And so we had to design the mechanical and electrical systems to be able to withstand the radiation environment that we'll be flying in. And so this is, I won't go through all of this, but this plays out in a number of ways. One is the total dose. And so we have, we try to minimize total dose to the components within the CubeSat by having thick aluminum shielding. And then also we're using this Z shielding material developed by NASA Langley, which is a layered tantalum titanium aluminum material to even further reduce the total dose within the CubeSat walls. And then we also have to protect against single event upsets. And so our kind of core critical systems like the CNDH, the power system, the radio are all designed to be more radiation tolerant and avoid destructive latch ups and minimize other types of single event effects. And so we also have watchdog timers on all these critical components. And so the power system can reset the processor if it thinks things aren't behaving. The processor can reset the radio can reset the power system and the processor through a ground command. And so we have a lot of kind of fault detection and correction systems in place to mitigate single event upsets and reset things if they try to clear these upsets. And then finally, I just wanted to mention that radiation on a budget is a challenge. And so one of the approaches we took to minimize these effects is to really try to keep the system as simple as possible and minimize the number of components on board that can have upsets. And so we don't have a GPS, we don't have a star tracker or propulsion. For our mission requirements, we didn't need them. And so we're trying to fly as kind of a more bare bones critical systems only type design. So just briefly our timeline where we are, we're kind of sitting here in the testing integration flat sat testing phase. And then hopefully later this fall and winter, we'll move into environmental testing and be ready for a launch late next year. And so one of the other questions that Matt asked me when we were talking before the GEM meeting was, why do I feel CubeSats are important to the future of our field? And so I actually, I am glad he asked this question. It made me kind of pause and think about it a little. And I think we're always looking for new things to measure in the magnetosphere, new ways of measuring different things, and then also new places to measure these from. And so with CubeSats, particularly higher risk and lower cost of these types of missions, they can allow us to probe regions we wouldn't normally send larger spacecraft to, like low altitudes, very low altitudes. You can have CubeSats be kind of sacrificial probes. They can also enable multi-point measurements or larger constellations that you couldn't afford with more costly, larger spacecraft. And then they let us test out new or riskier technologies. And so where are CubeSats going from here? There's a few different directions. One is actually to go even smaller. And so there are a number of different efforts to kind of get even smaller than the basic 1U 10 centimeter cubed CubeSat into things like thin sats or pocket cubes, or even these this Kickstarter campaign for these little kind of chip satellites. And so these let, you know, are more cost effective. They re-enter very quickly. I think a lot of high schools are getting involved in thin sat development, and you can kind of join different slices of these thin sats together to measure different things. And then the other direction is kind of the more capable, larger option. And so growing CubeSats, the standard started as a 1U 10 centimeter cubed, and now we're going into 3U and 6U CubeSats. There were the two 6U CubeSats that went out to Mars, the Marco CubeSats developed by JPL. And so these obviously cost more and take a lot more time and energy to develop, but are significantly more capable than where CubeSats started. And then, you know, you can even start imagining 12U and 27U, and whether these are now CubeSats or just small sats is one question, but kind of ESPA class small sat are now one direction that CubeSats are growing into. And so finally, with all these different capabilities, you can start imagining not just constellations of low Earth orbiting spacecraft, but small satellites or CubeSats constellations to probe deeper in the magnetosphere, like this kind of rendering of the MagCon concept study. So finally, I guess I wanted to emphasize that these different paths aren't mutually exclusive. You can kind of continue to branch out from here. So CubeSats started as this kind of one idea for educational and tech demo type applications. And from there, they've gone in all these different directions. You can continue to use them for education. There's lots of industry getting into small sats, making constellations. You can make them more resilient, larger, or go the other direction. But it's important to remember that each of these then means a slightly different thing. And so you can call them all CubeSats, but you want to specify what aspect of the CubeSats you're actually utilizing. And so if you're making it more resilient, just because it's small, it might not be as quick to build or as affordable to develop. And so each of these different applications means something different in terms of cost, schedule, and where they might fill a role in our science objectives. So with that, I thought I'd end on this plot, which I thought was pretty interesting. It's just the overall success rate of CubeSat missions over the past 2 decades. And so what you can see is that early on, there were a lot of failures. A lot of CubeSats that are dead on arrival or you never hear from again, or just that don't behave as you initially anticipated. And that's been improving dramatically over this time period. But what I thought was interesting is that you actually see this success rate kind of leveling out over the past 5 years. And what appears to be plateauing at about 75% success rate. And I actually thought this was kind of encouraging. I think I'd rather see it level out at 75% than go on to be 100% success rate, because it means we're still using CubeSats to try new things and to kind of push the boundaries of what we can measure or can do. And that we can use them to take risks that larger missions in our field really can't. So with larger missions, you need much higher probability of success, but CubeSats, it's, I hope to see that this, that we continue to use them in this kind of riskier, kind of boundary pushing way. And so with that, I think I'll end and open it up to any questions.
Okay, thank you, Lauren. So Matt, are there any questions for Laura from the Q&A?
Yes, there are. And the first one is from Ankush Bhaskar. How will the orientation of the spacecraft be determined and controlled?
So that's a good question, especially because we don't have a star tracker or things like that. We have sun sensors on every face of the CubeSat. And so that's one input into how we're oriented with respect to the sun. And then we have reaction wheels to point towards the sun and magnetorquers to dump the momentum from the reaction wheels. And so that's how we'll stay pointing to the sun throughout our orbit and spin up to be a sun-pointed spinner.
How do you deal with the shielding for the sat? Is the CubeSat expected to survive a strong, maybe out of the ordinary enhancement of relativistic electrons?
So that's another good question. With the mass limitations, we could only shield so much. So we definitely have thicker outer walls to the CubeSat than most would to help lower our total dose. But we're also baselining kind of the average radiation environment that we might expect to see. We can only do so well at predicting how the radiation belts will look and what their fluxes will be in 2 years. And so if there is a very strong event, it's possible it could knock us out. We haven't designed for the worst case scenario because we just can't fit that all into a CubeSat if we plan for every worst case. So we're designing for more nominal environments.
Okay, and what are, for your CubeSat success rate, what were the inputs for failure?
That's, I should refer you to the paper there, and I should, I'm not exactly sure. It's kind of hard to define. Often missions have partial success. And so that would, you know, they work and you talk to them, but they don't accomplish all your science goals. And so I'm not sure what the author there was counting, or, you know, it's a bit of a gray scale. But yeah, I can, the reference is on there and you can find it online. And so we should both take a look at it more carefully.
Okay, thank you. So we have, thank you, Lauren.
Great, thanks.
We have one more brief discussion today, and Adam will introduce our last speaker. Adam, we cannot hear you.
I apologize for that.
Okay.
Sorry about that. I had my headphones off. So we'll now hear from Drew Turner to honor our colleague and friend Sam Bingham. And this will be by raising mental health awareness. And this is especially important during the difficult times that we're living. So I'll give you the floor, Drew.
Thanks, Adam. Can you guys hear me okay?
Yes.
Perfect. So thank you, Adam, and special thanks to the GEM Steering Committee for allocating this time in the schedule. This is recent and unexpected tragic news that we're sharing here, but it's really driven us to hopefully start an effort here that benefits our whole community. So as many of you hopefully saw in the GEM Messenger last week, our community has suffered the loss of one of its own, for tragic reasons that we're always going to be struggling with, but we'll never really know. Our colleague and friend, Sam Bingham, took his own life sometime over the 4th of July weekend. While any effort now comes too late to save Sam, we hope that Sam's death will launch a movement in our community that may help others, both within our community and beyond. Through this effort to better recognize and acknowledge mental health, we will honor Sam's life and memory. Sam's mom and dad, who may be dialed in right now, have given us their blessing and support and have been so encouraging to us to engage in this endeavor. So I need to say special thanks to them for sure. And at this virtual GEM, we're also going to be taking time to remember Sam, both as a friend and as a colleague. So on Thursday evening, we're going to be holding an event to remember Sam and provide a small tribute to his science and contributions to our field. You can see the details here, and please see the VGEM website online for details on that remembrance and tribute event. Okay, so the unexpected suddenness and tragic nature of Sam's death has hit many of us really hard. And we're struggling to cope with just the senses of loss and grief. Those senses are natural. They're how our brain and body respond to trauma from a death of those close to us, especially one that's sudden and unexpected like this. Feelings that may be common include shock, numbness, disbelief, fear, anger, of course, sadness, and even some physical reactions. Those are all common to people experiencing grief and loss. If you are experiencing those, you should make sure to care for yourself physically and emotionally. It helps to express your feelings. It helps to participate in rituals and memorial services. And of course, feel free to seek the support if you're feeling overwhelmed, both from friends and family as well as from professionals if needed. And there are some good resources listed here on the slide for additional information. And these slides are available online on the website too. So don't feel like you need to write them down. So our work, as I think all of us are well aware, especially in grad school and our early career periods, can be very stressful under even normal circumstances. Yet, of course, nothing about the state of the world would be considered normal right now. These are truly emotionally and psychologically trying times. The world of humanity is suffering under several diseases. First, we have the pandemic, which has disrupted our lives, leaving us largely sheltering in our homes, socially distanced and feeling isolated. And of course, within our own community here, has caused our usual and frequent meetings, which I know a lot of us love so much, to cancel or to go virtual like this one. Then we're also facing the disease of systemic racism and broader social inequity that continues to plague us throughout so much of the world, and especially here in the United States. The ever-increasing political divides here and elsewhere in the world, plus the ever-increasing threats of global climate change, just adds so much to all of this underlying tension, anxiety, and despair. So understandably, many of us are struggling with mental health right now, and there should be no shame in that. Mental health is just as physical health. And I think all of us as scientists can appreciate that when we consider the brain as an organ and that it works through chemistry, it is physical. We would feel, I should say, no shame if we'd broken a bone, or we're fighting cancer, or we're managing diabetes. And we should feel no shame if we're suffering from anxiety or depression or trauma. Mental health carries a stigma in many cultures worldwide, including here in the US. And that prevents many of us from seeking and receiving the care that we need. There are many resources available. I'll show some in the next slide. And just remember, nobody's alone, especially in GEM, in our tight-knit community. And some stats here just to really put things into perspective. Some of these were actually compiled from Sam's mother, who works at the CDC. Suicide was responsible for more than 48,000 deaths in 2018, which resulted in about 1 death every 11 minutes on average. In that same year, 10.7 million Americans seriously considered suicide. 3.3 million actually made a plan to commit suicide, and 1.4 million actually attempted it. Suicide is the second leading cause of death in the United States for people between the ages of 10 and 34. According to a Harvard Crimson poll in 2004, 4 out of 5 Harvard students suffer depression at least once during the school year, and nearly half of them suffer depression so debilitating that they can't function. From a more recent Science article, 32% of PhD students are at risk of having or developing a common psychiatric disorder like depression. And from an even more recent Nature article, 36% of graduate students sought help for anxiety or depression related to their PhD. These are just incredibly challenging and mentally exhausting times, but we're all going through them together. And despite the necessity and vital importance of social distancing, just remember you're not alone. So here's some resources. There's the National Suicide Prevention Lifeline with the website here, and a hotline that you can call anytime. It's a free 24/7 confidential service. Considering the difficult times that I just mentioned, there are some really nice resources here posted by the CDC concerning mental health during the COVID-19 pandemic. And then, of course, counseling is covered under most medical insurance policies, and is also offered at many university campuses. Mental health therapist is an objective and empathic professional that one can really open up to without any fear of guilt, shame, or burdening. So especially in physics, but more generally, the expectation that one must go through severe yet concealed mental health trials to be successful is really dangerous and damaging to all of our communities. From that 2017 article in Science, this quote really stuck out. It's a public secret that fear of stigma, retaliation, or the expected negative impact on one's future career often inhibits people suffering from mental health issues to make it public. This lack of visibility is problematic because feeling isolated can cause one's mental health to deteriorate even further. It also means that there's less pressure on institutions and people in power to tackle the issue. As physicists, I'm sure we can all appreciate how nonlinear feedback works. By fighting mental health stigmatization, our GEM community can be an example of positive change and community support. Any successful models that we develop and implement within our community can be emulated by others, perpetuating positive change. Another good resource here is the National Alliance on Mental Illness, which is actually the button that I'm wearing right now, which says no with a K, science, and no with an N, stigma, mental health awareness. The NAMI site is right here, and it has some excellent resources for educating yourself, for how to engage in outreach, and for family support. And then Robert Allen set up this wonderful site that we hope our community will embrace. Please feel free to contribute to the discussion. The sites below, which again will be posted on the GEM website, you can download these slides from there, allow you to disclose and share your own experiences with mental health, either anonymously or in the open. And just remember this, the whole point of this is to show that we're not alone. There's already a few inputs on there from some of us that I helped put this all together. So that's what this is. This is a call to action. We're opening the door here to a community effort to improve support vectors for those suffering and to eradicate the stigma around mental health. We encourage you to reach out to friends and family and colleagues that might be suffering under the weight of these trying times, in particular anyone that might be feeling isolated. Learn how to identify, so educate yourself and learn how to identify those that are suffering or struggling, and reach out to offer your support. We're going to encourage people to, in our community, to volunteer to serve with us in this kind of ad hoc forum that we're putting together as a mental health ally. We suggest wearing a lime green ribbon at future meetings. Lime green is the color that's used for mental health awareness. With those ribbons, you can show that you've educated and trained yourself, are aware of available services and resources, and will serve as an intermediary between our community and mental health professionals for anyone that might need help. While we are not professionals in mental health, we can at least be aware of the pathways to those resources that are provided by mental health professionals and be willing to guide our colleagues towards those if they need it. Another thing that I'd really like to do with this is establish a forum between our respective institutes to evaluate the existing mental health resources and services, those programs at each of those institutes, compare and contrast those programs between the institutes, and then strive collectively to implement improvements across the board at all of them. So we just want to open up the floor. Unfortunately, with the webinar setting, we're unable to do that here. But what we'd like to do is there's the chat function here. However, I'd really point you to the Slack channel. If you look up the channel 0, support each other, we can keep the conversation going there. Please also see that Google document that Robert set up that we had the link on in that last slide, where we can share our stories as a community. Several are already posted there. Since I have a hot mic, I can share mine right now. I'm completely willing to share the fact that my mother has been suffering from and now actively managing bipolar disorder for as long as I've known and loved her. Due largely to that stigma that I talked about, she went undiagnosed for 62 years of her life. But now she's received the treatment that she needs and is on a prescription that helps her balance her moods. Myself, I've personally suffered from depression at least twice now in my life. My family knows of the struggles and challenges surrounding mental health very well. It's through both the love and support of my friends and family, including several of you here from this GEM community, and the service of professional counseling that I myself have been able to heal and come out of those dark phases of my life. And I have no shame in any of that. If anyone else would like to share their experiences, please see those. Please see that Slack channel, please see that Google document. And with this effort, while it might be too late to help Sam, by doing this, by actually engaging in this call to action, we can honor his memory by helping many others that are suffering in silence like he did. Sam was such a kind and gentle soul, and I think he would probably appreciate this endeavor. That's all I have, guys. Thank you so much.
Thanks, Drew. Indeed, this is a very difficult time for the community, for us all. And thank you for bringing this. Is a very important topic that we have to keep discussing, and having such open discussion is the best way to address and to move forward. So also a reminder that there will be a memorial for Sam on Thursday. Adam, would you like to add anything?
Just that there's a couple of questions.
Mm-hmm.
And so the first one is regarding the charts. Why aren't they online for downloading? We will ensure that we get them online, and we'll post a link in the Slack channel so that everybody can get to them. We had some issues with the system, but Chris and Jialin are working on that. And the other ones, we have some comments. So excellent presentation. This is not an isolated problem. Here in Brazil, we have maybe a worse number than yours. My question is, how can we do better to help everybody that are usually invisible for us?
So again, I'm not a professional in this at all. We have some on the line that I think are going to be available through the Slack chat. By the way, UNH and Dr. Robinson in particular has been really kind to help with this presentation as we've prepared it. The only thing I can suggest is just see some of those resources that we have the links to and learn what some of the signs are. And reach out to people that you think might be showcasing those signs. And also just continue doing this, continue having discussion about mental health and mental health awareness in open forums, because that builds awareness and that makes more people willing to come out and talk about it in the open, because we really need to just fight that stigma. There's no reason for it. It's outdated and it's hurting people. So we should do what we can in open fora to discuss and try to eradicate that stigma.
Thank you, Drew. That's all the questions that we have, Vanya.
Okay, thank you. So thank you all for joining. By the way, if you cannot see the participant list, we had more than 300 people online participating. So it is great. And we will continue this afternoon with the focus group breakout sessions. And also we have a poster session. So I would like to remind everyone to upload a PDF, and if they can also a video of their poster to the VGEM website. So with this, I would like to close. Thank you all for attending, and we'll see you this afternoon.